Let's talk about limit laws for sequences, in particular, the proof of the sum law. But before we talk about it, I want to talk about the reasons why we need these kinds of laws. So last time we proved that the limit as n approaches infinity of 4n cubed plus 3n over n cubed minus 6 was equal to 4. Now, that proof was very complicated and required some ingenuity. If we had a system for proving such things that involved having a rich set of tools, then it might be much easier for us to think through these proofs. And the tools that I'm talking about are the limit laws that allow us to decompose a limit into subproblems and then manage those subproblems and then deal with those in and of themselves. So the limit laws are going to take this form. If we have two sequences, a sequence an and a sequence bn, and we know the limit of the sequence an is a, and we know the limit of the sequence bn is b, then we can predict the limits of the sequence an plus bn, an minus bn, an times bn, and an divided by bn. And it turns out to be what you would expect. The limit of the sum of the sequences is the sum of the limits. The limit of the difference is the difference of the limits. The limit of the product of the sequences is the product of the limits, and the limit of the quotient is the quotient of the limits. And I have a little asterisk here. This is, of course, provided that b is not 0. It's perfectly possible that all of the terms of the sequence bn are non-zero, but the limit of those terms is 0, in which case you could get a 0 here, and then, of course, we can't divide by 0. This statement couldn't possibly be true. So if we have a rich set of tools like this, we can use them to solve problems like this more easily. We would have to do a little bit of preliminary algebra. The best thing to do would probably be multiply by 1 over n cubed on the top and multiply by 1 over n cubed on the bottom, so that this would be converted to the fraction 4 plus 3 over n squared, 1 minus 6 over n cubed. And then we would be able to apply the quotient law and the sum law and the difference law for limits in order to resolve this problem in a more methodical way that required less ingenuity. Now, what should be recommended to the student? If you're learning analysis for the first time, you need to be able to solve problems like this straight up without using these limit laws. You also need to be able to solve problems like this using the limit laws. So which is the right way? Both ways are the right way. But there's a third thing that's less obvious that you need to be able to do if you really want to understand how this analysis is working. And that is, the limit laws shouldn't just be handed to you on a silver platter. Here, use this, this works, trust that this is okay. The limit laws themselves should be subject to the normal rules of proof in mathematics, and you shouldn't take my word for it that the limit of an plus bn is a plus b. In other words, you should be able to prove the limit laws themselves. So last time we proved this, but that was very concrete. This time we're going to prove a statement which is the sum law for limits here in A. And this is going to be more abstract. And therefore, actually, it's going to be a little bit easier algebraically. We won't have to worry about these crazy fractions. But it'll also be more challenging because we won't have specific values to deal with. So that's the plan. We're going to prove the sum law for limits. Let's state the definition of the limit, because that's the only thing that's going to give us the power to do this. So the limit of an as n approaches infinity is the value L such that for every epsilon greater than 0, there exists a cap n such that for every n in the naturals, if little n is greater than cap n, then the distance between the term an and the result, the limiting value L, is less than epsilon. Again, in ordinary language, this means no matter how close you want an to get to the limiting value L, the proximity measured by epsilon, then there is some eventuality, there is some location after which all of the terms are within that proximity measure, epsilon, from the limiting value L. So that's what that definition means. We need to use the definition of the limit not once here, but really 3 times, because the sum law for limit is really about 3 limits. It's about the limit of an plus bn, but it's also under the assumption that we know something about the limit of an and we know something about bn. So this definition of the limit, phrased here for the abstract sequence an, needs to get used for an, it needs to get used for bn, and it needs to get used in the sense that we are assuming it for the sequence am and we are assuming it for the sequence bn. It also needs to get used for the sequence an plus bn in the sense that we need to prove that this definition applies to the sequence an plus bn and yields the value a plus b. So just like last time, we're going to follow the definition of the limit as it applies to the sequence that we're interested in, an plus bn in this case. And just like last time, we're going to be faced with a choice of cap n here, and we won't know how to choose it. And so we're going to just leave a blank and continue our work and see where the algebra takes us. Trying to not make the proof seem too magical, but discover it as we go along. So let's take the definition of a limit. Let's remember that it is assumed for an, it is assumed for bn, and we want to prove that this limiting statement is true for an plus bn, and that takes the limit a plus b. So let's begin a proof that the sequence an plus bn converges to a plus b. So if the limit of an equals a, that is, of course, as n goes to infinity, and the limit as n goes to infinity of bn is equal to b, then the limit of an plus bn is equal to a plus b. Okay, so having rephrased the sum law for limits here, then it'll be safe to erase it here, and we're going to begin the proof here. And the proof will begin the same way we began the proof for that previous more complicated algebraic example. It will begin in the only way a proof using the definition of a limit can begin. Let epsilon be an arbitrary number greater than 0. So let's begin. Let epsilon be greater than 0. And now the only natural way to continue, if we're following this definition, is to provide a choice of cap n. And now, as usual, I have no idea what to choose for cap n. And so I'm going to leave it blank. But then I know how to continue the proof. I need to demonstrate that the rest of this is true for that choice of cap n. And the only way to demonstrate, or the natural way to demonstrate that for all n something is true, is to let n be an arbitrary thing. So we're going to say, let little n be a natural number. Now I'm proving an implication as before, and so I will continue by assuming the first part with the idea of proving the second part. So we're assuming that little n is greater than cap n. So here we're just following our nose. The structure of this logical statement insists upon this as the most natural proof structure. Now I need to carefully apply this definition of the limit to the right sequence, and then I need to start reasoning about this thing. Now, we are attempting to prove that the limit as n goes to infinity of an plus bn is equal to a plus b. So the sequence involved is the sequence an plus bn. So instead of an here, we should have an plus bn. And we're attempting to prove that it's equal to the limit of a plus b, not L. And so in place of L, we should put a plus b. And then we will write epsilon for epsilon. So we're going to continue our proof, and we're going to say, and I think I'll begin it here because it'll all be part of one unit. We're going to continue our proof, and we're going to say, let's think about the distance between the sequence terms and the claimed limit value a plus b. So this is this term with the right sequence, the sequence an plus bn plugged in, and the right intended limit, the limit a plus b. And this is analogous to what we had before when we had the crazy rational function -4, and we tried to do a whole bunch of computation. And this needs to be eventually less than epsilon. So here's where I intend to just write equals, 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 and we'll do a long computation here. But just as before, and just in any such example, less than or equals is okay too, and less than is okay too. And so we can have a mix of less than or equals, and we can have a mix of less than, and so long as we have these symbols and they're all justified, and so long as we get eventually less than epsilon, then we will be able to say, okay, we've done it. We've proven that this thing is less than epsilon. Of course, ultimately, the reason we'll have done it is that for some reason, little n is greater than cap n, when cap n is chosen correctly. So we'll need to go back and fill in this details as we go. Now, here, I suggest we just follow our nose with some algebra. We've got an plus bn, a plus b. This thing rearranges in a natural way to be an minus a and bn minus b. So let's rearrange it and see what happens. This is an minus a plus bn minus b. Is this helpful? Well, let's find out. Well, this is an interesting term because this is the distance between an and its supposed limit a. And this is an interesting term, bn minus b, because it's the relationship between the term bn and its limit b. So let's try to separate them. So let me suggest this. I'll make an intentional error here and then fix it. Let's just divide this absolute value into a couple of pieces so that we separate the absolute values into two parts. Well, that's better. That's an improvement. That's easier to think about because this absolute value is something we'll be able to reason about using the definition of the limit. And this one, similarly, for the two limits that are assumed, namely this one and this one. But is this true? Is this true that the sum of the absolute values is equal to the absolute value of the sums? Well, I mean, sometimes, right? Sometimes the absolute value of 3 plus 5 is 8. And similarly, that's equal to the absolute value of 3 plus the absolute value of 5. So yeah, sometimes. But sometimes the absolute value of 10 plus negative 2, is that equal to the absolute value of 10 plus the absolute value of negative 2? Well, no, because this one is 8 and this one is 12. And so this step that we've taken here is not always correct. So sometimes it's good and sometimes it's bad. And how can we, so if it doesn't always work, then this step must have been an error. Well, that's okay, because this step is actually the content of the triangle inequality. Notice that we've got a sum inside an absolute value sign, and we're trying to split it up into a sum of absolute values. Here, this equation says 8 equals 8, so that's fine. This equation says 8 equals 12. This kind of logic can go off, it can go wrong, but when it goes wrong, this is always the lesser and this is always the greater. And so that means, in general, this is true. So this is just sort of falling backwards into a reminder that the triangle inequality is an available operation when we're doing these things and helps us to divide this absolute value of a sum into smaller absolute values. Now, we haven't yet used our assumptions here that the limit of an is equal to a and the limit of bn is equal to b. Those assumptions are surely going to come into play eventually. How will they come into play? They'll come into play because they'll allow us to control terms like an minus a and bn minus b in the definition of the limit, in the definition of these limits. So you might think here that I would go in here and I would say that this thing is less than epsilon. So would that be correct? And then this thing might be also less than epsilon, and so their sum would be less than epsilon over epsilon. That would be a natural thing to do, but it's not quite right. The reason I say this would be natural is because we know that the limit of an as n goes to infinity is a. We know that the limit of bn as n goes to infinity is b, and so the definition of the limit should tell us about the term an minus a being less than epsilon, right? And similarly, the definition of the limit should tell us that the term bn minus b absolute value is less than epsilon. So that seems natural, but that's not quite right. And the reason it's not quite right is that the definition of the limit is not just this statement that the absolute value is less than epsilon, but the entire logical statement that for any epsilon at all, that there exists some cap n such that for any little n, not necessarily the one that we've chosen here and not necessarily the cap n here, right? So the epsilon here is arbitrary, and the cap n that exists as an illustration for a given epsilon for this thing might be a different cap n because it's a different statement for this limit as it is for this one. So we can't just take this definition of the limit to be this part individually. We have to take it to be this reassurance that this statement is true when an goes in for an and a goes in for l. This statement is likewise true when bn goes in for an and b goes in for l. But it's the entire statement that is true for every epsilon. There exists some cap n such that for any little n, which is bigger than cap n, then this is true. So it's the whole statement which is true in each case. Okay, so that's why, so I'm explaining here why this naive replacement of an minus a with epsilon and bn minus b with epsilon is not quite going to cut it. There's another reason this is not quite going to cut it. The other reason is this gives us 2 epsilon, which is too big. We've overshot here. We're supposed to get less than epsilon, and this is going to give us 2 epsilon, which is going to, fail here. What we really need this to be is epsilon over 2. So that if this were an epsilon over 2 and this were an epsilon over 2, then we would make our goal. So I'm going to just very optimistically go in here and say that an minus a is less than epsilon over 2. But then you should be thinking that's madness because I have no reason to believe that an minus a is less than epsilon over 2. And that's partly true and partly false. I haven't quite given you a reason yet, but we can generate a reason why an minus a is less than epsilon over 2. So let's talk about that reason. We need to, at some point, invoke the definition of the limit as it applies to an minus a. Now, that definition says something about any epsilon, so long as that epsilon is greater than 0. Just as we can use an a plus b in place of L here, we can use any positive number we want in place of this epsilon if we are assured that this limit is true, which we are in the assumption that an goes to a. So knowing this limit gives us the freedom to choose our own epsilon and demand whatever n there might be, right? So there's a big difference between proving this definition and using it. When we prove it, we have to say, well, let's imagine epsilon to be arbitrary, positive, and I'll show you how to choose the n. But when we're invoking this definition because we know it to be true, then we get to throw our own epsilon into here and say, look, this is universally true for any positive epsilon, so it must be true for whatever I want to put in here. And then whatever I put in, there must be some cap n. We are assured, this definition assures us that there must be that, and then this thing must work for all little n greater. So what we want is we want an minus a to be less than epsilon over 2. And so this is going to be logically a little bit out of order, but I think it's natural in the way that we discovered the proof. So what we're going to do here is we're going to put a star here. And this star is kind of analogous to the logical debt that we incurred in the previous lecture when we said, let's just assume that little n is greater than 24, for example. But it's going to be a little bit deeper what we do. What we're going to do is we're going to say, I want an minus a to be less than epsilon over 2. And so let's feed an epsilon over 2 into the definition of the limit and demand that cap n. So here, what we're going to do is we're going to apply the definition of the limit of an equals a to epsilon over 2. So then there is some n such that for all, well, let me phrase it in the same way, for all natural n, if n is bigger than n, then an minus a absolute is actually less than epsilon over 2. So basically, I'm saying, okay, if this limit is true, then let's put your money where your mouth is. Let's give me that cap n. Okay, so that reassures us that there is some cap n. And because I'm sneaky and I know where this is going, I'm not going to call it cap n. I'm going to call it n1. I could call it na. That would be a natural name for it too. And then I'm going to refer to it here as n1. So there must be some n1 for which this distance is always forevermore less than epsilon over 2. And then I'm also going to assume that our little n, this one, is, let me actually say provided n is greater than cap 1. So n1. So here basically what I'm doing is I'm saying, I don't really know where it will be, but there will be some cap n beyond which, for all n greater than cap n, this absolute difference is going to be less than epsilon over 2. And I'm just going to, I know that exists. And then I'm going to furthermore assume that this n we chose in the beginning of the proof is going to be greater than n1. And if it is, then this inequality, an minus a less than epsilon over 2, is justified. So this is not completely logically forwards. We'll have to do a little bit of rewriting in order to make this work. Now, what about this one? Well, that's going to work exactly the same way. So you get the idea now. So what we're going to do here is we're going to apply the definition of the statement limit bn equals b, that is, of course, as n goes to infinity, to the value epsilon over 2. Basically, we're saying, okay, it's true for any positive epsilon. Epsilon over 2 is a positive number, and so there must be some value n. And what do we get when we do that? So we get there is some cap n2, so that whenever any little n is greater than cap n2, then we get, I have abbreviated it again. Let me rewrite that in the normal way. For all n in the naturals, if n is greater than n2, then bn minus b absolute value is less than epsilon over 2. So here we are invoking the assumption that the limit of bn is equal to b. We're invoking the definition of the limit with a bn in place of an and a b in place of l. And we're throwing into that definition the particular value epsilon over 2, which is anyway a positive number and can be placed in terms in the place of epsilon over here. The definition then guarantees us another cap n, which I'm calling n2, because it's different from this n1. At least it's potentially different from this n1. So then it exists. And then I'm going to say, and this is sort of the same star all along here, the star that justifies this key less than, then I'm going to say provided this less than is true, provided that n is greater than n2 as well. So like a lot happened here in this magical step, but the end resolution is that we end up with an epsilon, which is exactly what we need. So that may seem a little bit magical, but we've justified each of these by applying the definition of the limit. Now, let's talk about the way this proof has to be structured in order to be a proof that that really works here. N cannot, so last time when we did this complicated algebraic example, we said to ourselves, well, this proof only works provided all of these pieces of logical debt, all of these provisos that we've made in terms of little n are simultaneously true. And so we took the eventual n to be the maximum of the required thresholds, the maximum of that 1 and that 2 and that 24 and that other value. So here, this step is only going to be true provided that little n is greater than n1 and provided that little n is greater than n2. And in order to guarantee that it is greater than both of those, the natural thing to do is to choose cap n to be the max of n1 and n2. So that when we choose an arbitrary little n, and then assume that little n is greater than cap n, so a simple consequence of that is that n is greater than n1, and I wrote that badly, and that little n is greater than n2. So what we're doing here is this gives us a proviso that justifies this inequality. This gives us another that justifies this inequality. We're packing them together into one by choosing cap n to be the max of those two special values. And then when little n is assumed to be greater than cap n, it is effectively assumed to be greater than both n1 and n2. This is a little unclear. It's greater than n1 and it's greater than n2. Now, that's basically the right idea of the proof, but that still leaves us a bit of a problem. And the problem is that the proof is written out of order in a way that chooses things after they exist or after they're chosen. The specifications for how we've actually created n are given after n is chosen. So let's go back to the beginning of the proof and let's see whether it is logical. And it's not quite. So we're trying to say, we're trying to prove this definition of the limit as it applies to an plus bn and the limiting value a plus b. So have we done that? Well, sort of. We've been faithful to this definition of the limit. We're saying, okay, I'm trying to prove that for every epsilon something happens, so I'm going to let an epsilon be arbitrary. and I'm trying to prove there exists a cap n, so I'm going to choose the value of cap n. I mean, that's the right thing to do. Right now is the right time to choose the value of cap n. But I'm choosing cap n to be the max of n1 and n2. And this is where we are in the proof, right? This is how far we've come so far in the proof. And if we read so far in the proof, then we don't even know what cap n1 is. We don't know what cap n2 is, and we don't know what's going on. So there's an error in the ordering of this proof because we're using the values of n1 and n2 here, but we're determining their values or saying that they exist over here. And so that's not going to fly. Also, there's the worry that, like here, we're introducing the little n, and one thing that we mustn't do is we mustn't choose the value of cap n to depend on little n, because that would be cheating. It's not clear whether we have, because so late in this proof we've determined the values of cap n1 and cap n2. And so there's basically a chronological logical issue with this proof, and the issue is that n1 and n2 are introduced back here far after they're actually used to determine the value of n. So how do we fix that? Well, it's easy, but I'm not going to rewrite everything. All we do is we introduce a little location here, and in between those, we place everything done here and everything done here. So if I had a fancier system, I would copy this up and place it in here, but just imagine that in your mind, please. So all of this logic here goes right there, and all of this logic here, identified in red, goes also right there before the choice of cap n. So that cap n1 and cap n2 are decided before cap n, which depends on them, is chosen. Does that solve our problem? Well, yes, so long as these things make sense in this location. And this is not just a trivial thing. They need to make sense when placed here. That means that they may depend on epsilon, because epsilon is chosen at the moment when that happens, but they may not depend on cap n, they may not depend on little n, and they may not depend on the terms of the sequence. So are we okay there? Well, we've applied the definition of the limit to this thing, and we've applied it to epsilon over 2. Notice, in order to apply the definition of the limit to the specific value epsilon over 2, epsilon must be chosen. That's okay. It is by the time we reach here. It's not here, but it is here. There is some cap n1, and this depends on the sequence an, such that this is true. So we're only using here information about the limit of an going to a, which is assumed to be true, and the particular value of epsilon over 2 in order to decide the value cap n1 by means of the definition of the limit here. That's the only thing we're using to choose cap n1. It's the definition of the limit, the assumption that an goes to a, and the particular value of epsilon. All of those things are free for use at this point because we have assumed this, we know the definition of the limit, and epsilon has been chosen at this point. And the same argument is true here. This depends only on the assumption that this limit is b, the definition of the limit, and the particular choice of epsilon, which has already been made, so can be divided by 2. So these things are dependent logically only on things which have been decided by the time we get here. If we copy these out of here, if we cut these out of here and paste them here, then we choose the values of n1 and n2 just in time to use their values as we define n. Then the rest of this proof becomes correct. And instead of saying provided, we could say because, right? We can change this after we give a reason why this is true, and we have now, we can say because n is greater than n1, and here we can say because n is greater than n2, and it is, right? Because it's assumed greater than n, which is the max of these two values, so it must be greater than both of those values. So this is our proof of the sum law for limits. It's rather abstract, and now that we've proven it once, well, in theory, we don't have to ever prove it again, and we get to use it in every single problem that has a limit of a sum. And so that's the joy of theorems. The joy of theorems is you do the work up front once, you do it right, you do it at the correct level of abstraction, And then you can use it on every single example forevermore. So, all right, there we have it.